Okay, we seem to have a red light, so let's go ahead and get started. So our question of the day last time had to do with work. So here was the responses to that. Interesting stuff. So we're going to continue our discussion of linked lists today. So we'll be back on the document camera. Let me make sure I can bring that up. Make sure I'm seeing the same thing that you're seeing. Okay. So I hope that you went to a section yesterday and practiced the problems that we had that involved little neighborhood type problems. Today what we're going to do is talk about loops. It's going to be kind of the introduction to this. We'll do simpler loops today. We'll do more complicated loops in Friday's lecture. And you'll practice the more complicated stuff in Tuesday's section next week. So I'm imagining that I have a variable called list, which is storing a reference to a node that has a 3 in it, which in turn is storing a reference to a node with a 5 in it, which in turn is storing a reference to a node with a 2 in it, with a null at the end. Yeah, that green pen seems to be a little bit weak. Maybe we'll try another one of the green ones, see if it works a little bit better. So obviously, if we had a very short list like this that had only 3 bits of data, if we wanted to do something, so let's write some code that's going to print out these 3 numbers, 1 per line. So, I mean, you could just print out list.data, list.next.data, and list.next.next.data. That would be the neighborhood, type solution for doing something like that. But I'm imagining that this list, could have 1,000 things in it or something. So we want to write this in a more generic way so that it'll work for any length list. We're going to want to have some variable that'll keep track of where we are in the list. Kind of, we start at the beginning, but then we'll kind of move forward. Now, if we used list to do that, we could, but then what will end up happening is that list will end up moving all the way through these things, and we'll lose track of these things. I'd said last time that you could think of these as being like helium balloons, and if list lets go of these different balloons, they all just kind of float away, and we have no access to them anymore. So we'd want to have a different kind of variable to do that. A common choice for that is to have, so we want a variable of type list node, a temporary variable. Sometimes we use a name like temp, but for a problem like this, we tend to use a name like current. So I'm going to say list node current is going to be assigned to list. So I'm going to have it starting at the same place where list begins. So we have a variable called current that this arrow that's here gets copied into current, so it's going to point at the same node. So sometimes when I draw pictures, people kind of wonder, this is interesting. I was wondering, I thought I was maybe seeing things a little off. It's black ink, but a green cap on this pen. Okay, let's try. I'm actually kind of interested in using green today, so anyway, it'll be fun. We'll have combinations of colors. Let's see what we get. This one seems to actually be green. Okay, so list node current starts at list. Now, when I have arrows pointing at a node like this, sometimes I've had students ask me, well, what does it mean to point at the left-hand side of the node versus pointing at the lower left corner? And the answer is it makes no difference. I'm just pointing towards a node, so pointing means pointing. So these are the same. They're both pointing at this node that has the 3 in it. So suppose that we had some kind of a loop. So I'm going to say while something, we don't know quite yet what the condition is going to be. So while something is true, that's interesting. Okay. I think actually that it is green, but being picked up as if it's black. Interesting. All right, well, in any event, doesn't matter. So inside of the loop, what we're interested in doing is printing things out. So I'm going to say system.out.println. And so what would we print? If current is pointing here, we'd want to print the value that has the 3 in it. How do we refer to that? That would be, there's kind of I usually ask the audience, and sometimes I get a certain wrong answer that's interesting, is that people will say list.data. And it's true, initially list.data is that value 3 that we're looking at right there. But we're trying to write this loop in terms of a current. So we want to write it in a more general way. So we want current.data. So we can say println, and normally I'd put it all on one line, but there's not enough space. So I'm going to say current.data. Println current.data. And then what are we going to want to do? We're going to want to move to the next node over. So we want to reassign current. And what do we want to set current to be? We want to set it to this little arrow right here. And that little arrow right here is stored in this box. How do we refer to that box? Well, if current is pointing here, that box is current.next. So we want to reset current to be current.next. And so and I guess actually what I should have done is, we were thinking about, the first time through this thing, it does the println of current.data. So it would have done a println of this value that has the 3 in it. So that would have been a first line of output that we produced. We set current to be current.next. So this arrow here gets copied into current. So now current is going to point at the same thing that this little arrow is pointing at. Current is pointing here, and we come back around the loop. We still have to talk about what to put in the test, but we'll get to that. If we come in here, now current is pointing in a different place, which means that current.data has a different meaning than it had before. Current.data had been the 3 before, but now it's the 5, because current is pointing here. So when we do a println of current.data, we're going to get 5 as the output. And then when we set current to be current.next now is this box right here that stores this arrow. So when we do that assignment, current gets current.next, this is going to be reassigned to point at the same thing that arrow points at. So now current is referring to the node that has the 2 in it. And if we come around the loop and we go in again, when we do a println of current.data, now current.data is this value 2 that's right here. And we set current to be current.next. Current.next now is this box right here that has a slash in it to indicate null. So that means that current, it's no longer going to be pointing here. Current is going to be reset to null. How about if I make a new little box just to make that clear? Current gets set to null. So it's not pointing at anything now. Current is just null. If we come back around the loop, if we allowed ourselves to go into the loop again, what would happen? We would do a println of current.data when current is null. And that's what gets you a null pointer exception, when you try to dereference null. So this is going to come up in the code that you end up writing. Null pointer exception is a very common thing that happens when we're doing linked list coding. You're going to want to pay attention to, it'll tell you the exact line of code where it occurred, and it'll tell you how it got there, kind of what was the method that called it, what line of code were you in for that, and so forth. But what you would know, if it tells you a certain line of code, is that somewhere in that line of code, you said null dot. You tried to dereference null. So that would be an error, to try to dereference null, because null means no object. So you can't, there's no reference to follow. It would be like placing a phone call when there's no phone number. So it's an error. You're not allowed to do that. So, that should suggest to you then what we want our test to be, that we basically don't want to execute when that becomes true. We want to do it in the other cases, but not in this case. So we could say while current is not equal to null. So while we haven't reached the point where current is null, we'll do the println of current.data, and we'll do current, it gets current.next. So this is a simple example of a list traversal using linked lists. So this is a kind of standard code that you're going to get used to. Now, we've been talking for a long time about what if you had an integer array called list, was a new integer array. I'm just going to say dot, dot, dot. You set up some kind of an array with some code that fills it in. The way that we would write this using the for loop, we've talked about an array traversal. The standard array traversal would be for int I starting at 0, I less than, and if it's an array called list, we'd go less than list.length, and then an I++. And inside of the loop, we would do something like system.out.println of list bracket I. So that's how we would have written this code if it had been an array instead. And my suspicion is that this code is pretty familiar to you now, the standard traversal. This code, I assume, is not familiar to you. So I wanted to spend a minute to just kind of show you the correspondence here. I don't know if it'll be helpful or not, but if this is something that you know, and this is something that you're learning, it's not such a bad thing to relate, something that you know to something that you're learning. So in the array case, we begin by setting an integer I variable to 0, because to traverse an array, we can use a simple int that keeps track of the current index. That a simple int is enough to kind of have a finger that keeps track of where you are in the array. You've got this long sequence of values, and you just kind of keep a finger on where you are right now. I'm at the 18th element, or the 101st element, or the 5,000th element. So a simple int is enough to do that. What that becomes in the linked list case is this line of code right here that says list node current is assigned to list. So kind of the equivalent in linked list code is to set a list node current to the front of the list. So that's kind of the correspondence there. Here, the way that we test to see whether there's anything more is we see whether I is less than list.length. That tells me whether this index is actually referring to something that is an element of the array. Once I becomes equal to list.length, we've exceeded the highest index. We've run out of things to examine because the indexing variable has gone beyond the last value stored in the structure. And the corresponding thing here is to test where the current is not null. That tells you that current is referring to something that is an actual node rather than having run out of data where current has become null. We end up doing a println of list bracket I. So here we use list bracket I as the way to refer to an element of the list using our indexing variable. Here we refer to current.data, current.data, excuse me, current.data to refer to the next bit of data in our structure. And here using the integer indexing, here using the reference, the current, and using the dereferencing dot. And we do the update here by doing I++, which moves the, very simple kind of update that moves bumps up our integer index by 1 so that we're looking at the index 1 to the right of where we were before. The corresponding thing here is current gets current.next. So what that becomes over here is current is assigned to current.next. So that's kind of the correspondence between array-based code and linked list-based code. So that might be helpful to kind of be thinking about in terms of understanding what it is that these different elements accomplish. I usually pause at this point to see if there's anybody has a question about this. And sometimes I get the question, sometimes I don't. But one of the things to notice is that I wrote this with a while loop, and I wrote this with a for loop. So one of the questions is, do you need to do that? Well, we know that we could have written the array style code as a while loop. You don't have to write it as a for loop. What about the other way? Can you write the linked list based code using a for loop instead of a while loop? The answer is yes, you could. So you could say for, and then kind of the different elements, you'd say for list node current is assigned to list, semicolon, current not equal to null, semicolon, current gets current dot next. That's a whole lot of stuff to include, in the parentheses for a for loop. And then inside the body, we could say system.out.println, the current.data. So you certainly can do that if you want to, but we don't tend to. The other thing, too, is that these tests, we're going to see this in Friday's lecture, these tests sometimes become a lot more complicated than what we have here. So it's just, it could be done, and, I've occasionally seen programmers use a for loop for linked list code, but most programmers do not. Most programmers, we tend to use a for loop for array-based code. We tend to use a while loop for linked list-based code. There's no particular reason that you have to do one versus the other. It's more a matter of personal style. Okay, well, so that's an example of a simple loop. I showed you this last time where we had a list node class that keeps track of our data and our next, and it had our 3 different constructors. I pointed out that this is kind of the constructor that is getting executed in all of these different cases. It's the constructor that takes both the data and the link to the next thing and sets those fields. This one that gives just the data calls the other constructor using the this paren notation, and it passes in the data and a null. Here we have a 0 argument constructor that uses 0 and null to call that other constructor. So this is kind of these 2 constructors calling that 3rd constructor. And that's the way we're going to want you to write things in the future. You won't do that on homework 2 because in homework 2 the 2 different constructors are quite different. But we'll remind you of this when this becomes relevant to code you're going to have to write for homework. But that's going to be the pattern we're going to want to follow. But given the node class, what we're going to want to create is a public class that's going to correspond to our array int list. So what we're going to have is a linked int list class that's going to be built on a linked list rather than an array. So how are we going to do that? So I mentioned that we have public fields here, and I'm going to talk about that in a second. But we're going to want to make sure that this class is encapsulated well. So any fields we introduce, we're going to want to have be private for our linked int list class, because this is the class that a client is going to access. So what do we want to have? What do we have as fields? And again, it's too bad. I often get really interesting suggestions from students about what to have as elements of the class. Sometimes an interesting answer that I get is that people say you want an array like element data, because that's what we had with array int list, right? Is we had an array that kept track of data. Well, but this is a different approach. We're not keeping track of of data using an array. We're doing it with a linked structure like this. So if you had a list that had these 3 things in it, what do you need to keep track of in order to be able to access those 3 different elements of the list? So I get, again, interesting suggestions from people, and some people kind of notice right away. Some people don't notice right away what's going on. But basically, as long as I have a reference to the first thing in the list, I can get to everything else in the list. Because, then I'd have access to this one, and then I could do a next to go to the one after it, a next to go after that, and so forth. So I'm going to want to have a field of type list node that keeps track of the first thing in the list. And so I'm going to call that front. I could call it whatever I wanted, but I'm going to go ahead and call it front. So instead of having a variable called list, I'm going to have a field called front that'll store a reference to this first node. And it turns out that with all of those links, I can just kind of go from there to the next one, the next one, the next one, the next one. No matter where something is stored in the list, I can always get there from the front. So if I have access to the front, I have access to all of them. So this is going to give me access to all of the different nodes of the list. What else might I want to have? So one of the suggestions that people will often make is, why don't we store the size of the list? And that's an excellent suggestion. That it's like what we did with the letter inventory, is that instead of having to try to compute the size, why not store it and just kind of keep track of what the size is currently? So that makes a lot of sense, and any sane implementation of a linked list would store the size. But I want to keep things simple on purpose, so I'm actually not going to store the size. I will show you a nice version of linked list at the end of the quarter, and it has a size field. Because as I said, it's absolutely true that you'd want to keep track of the size and remember that. So instead, because you can always compute the size. You can compute the size by starting at the front and then just kind of counting. 1, 2, 3. It took me 3 things to encounter the end of the list, so I know the size is 3. So that's actually going to be a problem that I ask you to work on in section tomorrow. Basically all of the questions in section tomorrow are going to involve implementing different methods of the linked int list class that match methods that we had in the array int list class. So we certainly are going to want a size method, but we're going to do it in the inefficient way. Instead of storing the size, we're going to actually compute it by starting at the front and then just going to the end and counting as we go. Is there anything else you might want to keep track of? And I often have people who recognize that keeping track of the end of the list is a useful thing to do as well. If you had a reference to what was at the end, then it would be very easy to add something at the end. Wouldn't be easy to remove because we'd have to kind of recompute what the end of the list is, but adding at the end would be easy because I'd have a reference to the current end of the list, and then I could just attach something new at the end. So keeping track of the end of the list would be a helpful thing to do, and any sane implementation would do that, and the one I'll show you at the end of the quarter is going to do that. But again, we're kind of not doing, we're doing something simpler for now. So the version that I'm going to do, I'm not going to keep track of the end of the list. That's going to make it a little harder. Let me just kind of point out, though, that if, having a reference to the front of the list means that it's very easy for us to remove what's at the front. So we have a very quick remove at the front, and we can update the front to be this one over here if we remove this. And if we had a reference to the end of the list, it would be very easy and quick to add something at the end and reset the end of the list so that it was pointing at that new thing that we added there. So removing at the front and adding at the back are very fast with a linked list, and that's why it's a very good implementation for a queue. Those are the main operations with the queue, is removing at the front and adding at the back, and the linked list would be very fast at those 2 things. So storing reference to the last element of the list would also make a lot of sense. It's a good idea, but we're not going to do that. In fact, this is going to be our one and only field. We're going to keep track of the front of the list, and that's it. So that kind of gives us a lot of interesting little problems to solve in order to be able to get the functionality that we want. So I'm going to put a little ... here to indicate that there are various other methods here. We are going to write one of those methods in the lecture today as kind of the last part of the lecture. And then, as I said, in section tomorrow, the different section problems involve writing other methods of the linked int list class that match the methods that we wrote in the array int list class. We're going to write appending add, the add that adds at the very end of the list. But in section, the problems then will be things like adding at an index, removing at an index, computing the size, finding the index of a value in the list. So that'll be the section problems tomorrow. Now, let me say a little bit about what's going on with these public fields. So what we're going to make sure is that we're going to have a bunch of public methods here that a client would use when working with a linked int list. We are going to make sure that none of those public methods allow a client to access a node. The client won't even know that this list node class exists. So that means that the list node class is entirely on the implementation side of things. That it's used in the implementation, but the client has no way of even knowing that such a thing exists. So the client will have no access to nodes, which means that we can relax and have public fields here. An analogy that I use in the book is that I say, well, imagine that I was going to hire somebody to paint my house. And you could imagine I talk to different contractors, they make different bids, and they tell me how it's going to go. So I talked to one contractor who says, well, the day that we paint your house, you should wear old clothes because, these cans of paint get a little messy, and, you might get some paint on your clothes. So, don't wear nice clothes that day. That's, one contractor. And then I might talk to a second contractor who says, well, the day that we're going to paint your house, you should just leave. We'll do all the painting, and then you come back and it'll be done. And there'll be no possibility of you getting paint on your clothes because you're not even going to be there. This isn't a perfect analogy. Maybe the first contractor is cheap enough that I actually would go with the first contractor, kind of depending upon the prices. But in general, I like the idea of the second contractor more. That's why I'm hiring someone to paint my house in the first place, is that I don't want to have to do the work. I don't want to get my clothes, dirty and so forth. But it's common, if you kind of see people painting, it's common that the workers who are working on a project often get paint on their clothes. They tend to wear work clothes where it's okay that they could spill a little bit of paint on their clothes. So, it's kind of okay that there can be messy cans of paint, for the workers who are doing the actual job, as long as the client doesn't get any paint on the client. So that's going to be the idea, is that these are like messy paint cans or whatever that the workers use in implementing the different methods of the linked int list class, but the person who, the client of the linked int list class never ever sees that, can't ever get any paint on them because they don't have any access to the nodes. They don't even know those nodes exist. So that's an analogy. Maybe the better argument, if you're interested, is if you look and see what professional Java programmers do, they tend to do it this way. They tend to have node classes that have public fields. So they tend not to encapsulate a node class that is entirely on the implementation part of this problem, of this solution. Okay, so as I said, we're going to, in the rest of the lecture today, the problem that we're going to talk about is how to write the appending add. So the method that we're writing is public void add. And remember that it takes an integer parameter, how about if we say value, some value, to insert at the end of the list. So we're going to fill in this ... And then this is going to be one of the things that goes here. It'll, the appending add is going to be an example for us of a method that is part of our implementation of the linked int list class. So where do we begin? I'm going to think of what I consider to be a somewhat typical kind of case. So suppose that we've got our field called front, and front is referring to a node that, what did I want to do for this example? I wanted to have, so I want to not have to redo my notes for this, a node with a 3 in it that refers to a node with a 5 in it that refers to a node with a 2 in it. So suppose that that's what we have in our list right now. And suppose that we call the add method passing in a 17 for that value. So what I would like to do, this is a 3-element list right now. I want to change it into a 4-element list where the 17 is at the end. That's what I'd like to do. Well, how do I do that? Well, let's think of something that would be like what we did here, where we wrote a loop that kind of went through the structure. Now here we were printing the data as we went along. Here we don't need to do anything with the data as we get along. We just need to move to the end. So we don't need the line of code that's going to be doing the current.data manipulation because we're skipping past all of that data. We just want the current gets current.next part. So let's write some code that does that. So I'm going to say list node current is assigned to the front of the list. And then I'm going to say while current is not equal to null. And again, we don't need to do anything with the data. All that we need to do is to say current is assigned to current.next. We'll move forward in the list until we get to the end. So we keep doing that until we get to the end. And then what do we want to do? We want to add something to the list. So I'm going to say current is a new list node that has that value in it that we're trying to add. So remember that I had said that, that was over here on this piece of paper, that the add method is taking a parameter called value. I mean, in my example, I'm saying suppose it's 17. So we'll make a brand new node that has that 17 in it in order to add it to the list. This code that I've written here is a very important wrong answer, a kind of a good wrong answer. I often make this joke when I have class participation. I encourage people to give me answers, and I like it when someone gives me a good wrong answer. A good wrong answer is one that it's not right, but somehow the logic of it appeals to people. It's kind of a common wrong answer, something that people tend to think works. So this is code that people think is going to work, but it doesn't work. And it's very important to understand that it doesn't work. That's kind of the main point I'm going to try to make in the rest of the lecture today. What would be going on here? We have our variable called current, which is like front, that can store a reference to something, and we initially set it to be front. So I'm going to just use my pen for this rather than trying to draw arrows. That I'm going to have current kind of pointing upward at that node with the 3 in it. So what does this code say to do? It says, well, current is not null. Well, current isn't null. It's pointing at the node with the 3 in it. So it sets current to current.next. So the first time through the loop, current would get reset so that it's pointing at that node with the 5 in it. We come back around. Still not null. And so it sets current to current.next. Current.next is now this arrow. So current is pointing here at the node with the 2 in it. And that's still not null, so it sets current to current.next. Current.next is null in this case, so we set current to be null, we come back around the loop. Current has become null, so we break out of the loop. Okay, so this null got copied down to here, and that caused us to stop going through the loop. Because we did what we wanted. We saw the 3 different nodes, we got to the end of the list, and now current is null. Then we're trying to attach something to this list, so we go and we make a brand new list node that has that value we're trying to insert. So the 17 that we're trying to insert, we would make this brand new list node, and then Java returns a reference to that brand new list node that it just constructed, and we say store that reference in this variable called current. So reassign current so that it's got the reference to the node that it just constructed. So there's current pointing at this node with the 17 in it. And the question is, have we added it to our list? The answer is no. The list was a 3-element list, that's got a 3 and a 5 and a 2 in it. And it's still a 3-element list that's got a 3 and a 5 and a 2 in it. So what we've done is to set up a variable called current, which is a local variable that refers to a brand new node, but that brand new node has no connection to the list that we constructed over here. So, and this is a very, very important thing to understand. I'm not quite sure why people think this is going to work, but it's common. A lot of students seem to be confused by that. So let me mention an idea. I'm going to repeat this idea in the lecture on Friday. To change a list, there are only 2 things you can do that would change a list like this. One of them is to change front. So we have this field called front that's keeping track of the front of the list. Right now, front is referring to this node that has a 3 in it. If we rearranged front, say, so that it was referring to the node with the 5 in it, well, that's a different list. Or if front was referring to this node with the 17 in it, that's a different list. So reassigning front is going to change the list. So that is definitely one of the 2 ways that you can change a list. The other way of changing a list is to change one of the dot next fields. And it may seem odd that I mean, they're really called next, these fields. It may seem weird that I'm putting a dot in front of it, but I'll try to make that clear in the examples that I'm going to give, that you'd have to have a line of code that is somehow accessing something dot next. I mean, it might even be something dot next dot next dot next or whatever, but there's got to be a dot next in there in order for it to be accessing one of these fields. So in this list here, there were 3 different nodes. So that's a dot next field, using my terminology. That's a dot next field, and that's a dot next field. If I changed any of those 3 things, then that would change the structure of the list. That's rearranging the structure of the list. There's so many analogies that I've seen people use for this. Some people I've seen people who like to think of this as being like a necklace with beads that are kind of connected to each other. And if you kind of break one of the links and put a new bead in the middle, of the necklace, now you've got a change to the structure. But you'd have to rearrange those actual connections. Some people, I've seen people, there's a game that people in my generation played called Barrel Full of Monkeys, I think it was called, where you kind of have this monkey is connected to this monkey, connected to this monkey, you kind of have this, sequence of 3 monkeys. And if you disconnect one of those links and put a new monkey in the middle, that could be rearranging things. For me, for some reason, when I first heard about linked list, I have always imagined it in the same way. I have always thought of these as being like train cars. Maybe it's because, my brothers and I played with, toy trains when we were kids. And so, and they just kind of looked to me like train cars. So, and you connect together your different train cars. So there's a connection here that has these 2 cars connected to each other, a connection here that connects the caboose to the car. And you know that no matter how many of those train cars you have, if you grab the connection for the front train car, you can pull the whole train along by pulling that, because they're all connected to each other. And if you want to change your train, the train is a sequence of cars, right? You could imagine breaking one of those, kind of disconnecting, these 2 cars. You might scooch them apart and put a new train car in the middle and then reconnect it, rearrange those links. So, this would be like having a train car off to the side that has no connection to the train itself. So I've got kind of these 3 cars hooked together to form a train, and then off to the side I've got another train car, but that train car isn't connected to these in any way. Current is a local variable, and what happens to local variables when a method is done executing? They go away, so current would go away. That would mean that that we don't have this variable current anymore that's holding on to this helium balloon. And what I keep saying about the helium balloons is that once, if nobody's holding on to it anymore, so once current disappears because the local variable goes away, this balloon floats away. So it never ends up getting connected to these elements at all. So that's kind of the really important thing to understand. So we want to rewrite this code so that it's going to do the right thing. So how do we do that? Let me mention two more ideas that I use. One of them is, so what I did here and in the picture that I drew here is that I kind of had a variable current that was in one spot, and I just drew arrows to point at different things. Well, that's not kind of the way that I tend to visualize it, and I don't think it's the way that most programmers tend to visualize it. Instead of thinking of current as just kind of sitting down here with the different arrows, I tend to think of current as being something that is actually on top of a node. So that when you say list node current is assigned to front, I kind of think of it as current is positioned right here now. Current is sitting on top of that node with the 3 in it. And when you say current gets current.next, what ends up happening is current is hopping from one train car to another. I'm abbreviating it as cur instead of current. I hope you'll allow me to do that. So it's kind of like it hops from here to here. So now current is located here. So I actually think of this variable current as physically moving through the list from one to the next, to the next, to the next. So I find that a useful way of thinking about it. And I also anthropomorphize it. I've talked about that idea, thinking of it as being like a person, is that I kind of imagine that current is like a person on top of a train car. And for some reason, I've always thought of this as being like what you'd see in a James Bond movie, where Bond is on top of a train car and maybe some bad guy is trying to get Bond or whatever, and he hops from car to car to car. I've actually used this analogy for many years, and it was a fairly recent Bond movie where I think the opening scene, Bond is on the top of a train, hopping from car to car. It's not a perfect analogy because Bond could move in either direction, so Bond could move forward, and you can't do that in a linked list structure like this. You can only move in the one direction. But anyway, it's still not such a bad idea of thinking about that. So what did we do here in writing this code? We basically said, okay, put James Bond on top of the first car, and then while there are any cars left, have Bond hop from here to here, have Bond hop from here to here, and then have Bond hop from here off of the train, so that Bond is not on a car at all. Bond is hopped off of the train. And I kind of imagine Bond, standing there saying, wait a second, I wanted to attach something there. And the train is going away. Come back. I wanted to do something with that. So you don't want to let Bond hop off of the train. So there's a principle that's at work here that the TAs and I often refer to as stopping one early. So you'll hear that description a lot. The idea of stopping one early. What I want to do is I want to stop with Bond on top of the caboose, on top of the last car. I don't want Bond to jump off the train. I want Bond to stop here. So I've got my variable called front, my field called front, that's referring to a node with a 3 in it, that's referring to a node with a 5 in it, that's referring to a node with a 2 in it. And I'm trying to get to a situation where Bond, where cur, is going to be positioned at that last node right there. So how do I accomplish that? Well, I begin list node current is assigned to front. That's the only choice we have given the way that I've decided to have us implement it. We're not keeping track of the back of the list as a separate thing, but we'll change our while loop test. There's a special property that this node has that no other node has. And that property is that current.next is null. So I'm going to say while current.next is not null, I want to say current gets current.next. Current is assigned to current.next. So a different test. This is kind of the stopping one early test versus the test where we were just doing current. And after the loop, if we stop with current being positioned here, I'm still going to make a new list node that's got my value, my 17 in the example that we were talking about. I'm going to ask for a construction of a brand new node that's got the 17 in it. So I still want to do that. But then what am I going to want to do with the reference that's returned to that? I'm going to want to set current.next to be that. So I'm going to set current.next to be this new list node. So current is here. Current.next is this box right here. That's an actual link of the list. And so when I say that .next field should be changed to point to the node with the 17 in it, now I've made a 4-element list. Now it's actually part of the list. So I'm going to kind of, this will all be in the notes for today so you can study it. But I wanted to emphasize one idea, which is this was the line of code that didn't work, saying current is assigned a new list node. This is the line of code that did work, setting current.next. That's why I refer to these as .next fields. Setting a .next is something that can work. This works, this does not. They look very similar, and it's very important for you to understand why one of them works and the other one doesn't. The pictures tend to kind of tell that story. I've had students sometimes tell me they never understood those pictures. That's a problem too. If you don't understand those pictures, that's something to fix. You're not going to be able to do linked list coding. None of us can do linked list coding without being able to draw appropriate pictures. So this would be something worth studying, talking to a TA about in section or in office hours if it's still confusing. Very important to understand. That's kind of the key idea from today's lecture. All right, I want to do one last little thing in the last few minutes. I mentioned that I tend to like analogies of thinking of things like a train car. I like physical analogies to things. So I kind of like the idea of thinking of nodes as being actual things. So if I was going to try to put together the list that has the 3, 5, 2 in it, isn't that what? Yeah, 3, 5, 2. Then I'd have a node that has a 3 in it. And if I wanted front to refer to that node, then I imagine that there's a connection like this that's been set up, that front has a reference to that node. And if I have another node that's going to have 5 in it, then I would connect it in a similar way to this spot right here. And now I've got this node being connected to this node. And then if I wanted to have another node that had a 2 in it, I would connect this to here. And initially this would be null. And so I kind of imagine this as my list. And, as I said before, if you have the front of the list, I mean, it's all connected to the front. You can get to everything from the front. And it's like that train car, the train cars that I had been talking about. And so you can imagine current as being something that moves, initially it's positioned, to the first node, and then current gets current.next, and then current gets current.next. And if we let current get set to the null that's here, current would kind of be this, it would have jumped off of the list, and we would reset current to point to some node here that has no connection to the train, to the list that we formed here. Instead, we want to stop when current is positioned here, so that then when we refer to current.next, we're accessing this right here, which allows us to connect that extra node here. And that's when we make the actual connection. I guess I could do the little taping right here, that this is getting reset to be our node that had the 17 in it, and it's got a null. So that's how we actually change it, is by having current refer here so that we can refer to current.next and have it set to this node that we just added right there. So that's an analogy that I find helpful, is just kind of thinking of them as physical objects. In fact, I've sometimes had students come up after class and talk to me about this, and referring to the picture can often be very helpful in trying to explain to them what's going on. I had a student once, I think, who took pity on me for my pathetic props in class, and she made a version for me where I can kind of keep track of a train car where this is connected to a node that has a 3 in it, and this is connected to a node that has a 5 in it, and this is connected to a node that has a 2 in it. And really I should show this as null, but indulge me, imagine that that's set to null. So she kind of set up the little train cars for me, and she even gave me James Bond, so that I've kind of got James Bond, I set James Bond to the same thing that front is referring to. So James Bond is on top of that car right there. And then that's not the caboose, so we do current gets, current.next. That's not the caboose, so we do current gets current.next. And while James Bond is connected here, James Bond says current.next should be set to a new node that would have that 17 in it. And now you can kind of see that it is connected into the actual train. So anyway, that was a very nice little set of props that she made for me, and so I thought I would show them to you guys in case that helps you at all to understand. I didn't mention that there was a special case we didn't deal with. This is in the notes, that we didn't deal with the case where front was null. I almost forgot to mention that. This code is going to give a null pointer exception if current is initially null. So you need an extra case in order to make this work properly that deals with the empty list case where you reassign front. One of each, front being changed and a dot